Okay, I think we'll start. So welcome to the latest seminar in the Focus Week on Painlevé. This session is being recorded, so if you don't want to be captured and when given a question, then please turn your video off and please go to mute. You can also switch off the live transcript using one of the preferences if you don't want to see the live transcript actually appear. So it's a pleasure to welcome today's speaker, Nalini Joshi from the University of Sydney. She's a well-known expert in Painlevé equations, someone who I've known for a long time. Nalini did her PhD under one of the gurus of the topic, Martin Kruskal, and we look forward to hearing her talk today on what do we know about solutions of Painlevé equations.
Thank you very much, Peter. And I want to start by thanking the organizers of the program at the Newton Institute, particularly Chris and Ines, for their welcome to the program and for inviting me in the first place. I want to thank the Newton Institute for giving me a Rothschild Fellowship to participate in the program. I just feel so sad that I can't be there in person. What I'm going to talk about is the Painlevé equations, but as many of you know, my interest has become more and more focused on the discrete Painlevé equations. So by calling it the Painlevé equations, I mean not just the classical continuous differential equations known as the Painlevé equations, but also the discrete Painlevé equations, which are an incredibly beautiful series of objects that I hope more and more people will get interested in. In some ways, giving an overview of this topic is like showing you a wild raging waterfall somewhere in the wilds of some continent and only being able to bring a little thimble full of water back to share with you. So in a sense, this hour-long talk is not going to be able to make to really give a very good snapshot of the riches of this field. So I just talked with Ines, and if anybody is interested, I'd be happy to give more talks or expand upon any of the points that I touch upon in today's talk. So please let me know if you'd like to have that conversation. Okay, so the main question that led to the discovery of the Painlevé equations was the search for new functions. Near the end of the 1800s, the theory of elliptic functions was becoming extraordinarily rich, built upon the building blocks that Abel, Jacobi, Weierstrass, and many others had been building throughout that century. But knowing about elliptic functions, abelian integrals, functions that are parameterizing curves of higher genus, led to some key questions in the minds of mathematicians active at the time. One of those key questions was, if the elliptic functions and hyperelliptic functions can be described as solutions of differential equations, are there more differential equations that will lead to even newer functions, well-defined newer functions, functions that go beyond the elliptic functions that they knew about at that time? In other words, given a class of differential equations, how can you identify those ones that are going to be rich enough to have solutions that go beyond the set of known functions at the time. What new functions existed that generalized elliptic functions? And if I can make this work, there we go. One of the key observations in that questioning, in that development of the theory, came from Sofia Kovalevskaya, who is one of my heroes, who lived a tragically short life, even for those times. And the key observation she made came about when she was studying the question of how to solve the equations of motion that govern a rotating top, which is rotating with the fixed, around a fixed point. And in her way of phrasing the problem, I mean, obviously she and others were aware that Euler and Lagrange had already solved this problem for certain specific cases. So if you think about the moments of inertia in the three principal directions as say A, B, and C, corresponding to X, Y, and Z coordinates, Euler solved the case when the center of gravity of the top, the spinning top, lay at the origin. Lagrange solved the case when A is equal to B and the center of gravity lies on the Z-axis. And the way they'd solved these particular cases relied upon elliptic functions. Now, elliptic functions, as we all know, are meromorphic functions in the complex plane, which are doubly periodic functions. So how did Kovalevskaya tackle the problem of searching for other cases that could also be solved in this way? By observing the fact that these earlier cases had been solved through elliptic functions, she imposed a new idea. She asked whether there were cases for which solutions could be, all solutions could be meromorphic around all movable singularities. Movable in this context means that the position of the singularity is changeable as a function of initial values given for the motion. And by imposing this condition and then finding the necessary conditions and then observing how you could identify the resulting functions, she was able to solve the problem completely in another case. And the case is when the moments of inertia, A was equal to B and both were equal to 2 times C, the remaining moment of inertia. And also the vertical coordinate of the top lay on the horizontal plane. So she found, so this was an incredible piece of work for which she won a major prize of the Academy of Science in France. But the key observation I want to point out here is this new idea that all solutions needed to be meromorphic around movable singularities, because that was the foundation of the next several steps that were taken by French mathematicians near the end of the 1800s. And the key person in that investigation was Paul Painlevé. Now, many of you already know about his life, know that he was not only a mathematician, but also very prominent in the French political sphere. He was a minister of war during the First World War. He was also prime minister briefly twice, and so on. This picture of him is from around 1902, when he was writing major papers on the subject. So he searched for second order ordinary differential equations that had new functions as solutions. And to define solutions of these equations globally in the complex plane, the idea he imposed was that, like in the case of the elliptic functions, like in the case that Kovalevskaya studied, that solutions needed to be single valued around all of their movable singularities. Otherwise, there will be too many, there would be an infinite number of ways of defining different solutions. And so then he went ahead and deduced necessary conditions following on from this key assumption and discovered certain differential equations which did have new solutions. And it turns out that for these cases, all the movable singularities are in fact poles. But he missed some cases. And in fact, the capstone of his discovery, the biggest piece of the puzzle, was found by Richard Fuchs. Richard was Lazarus Fuchs's son, and Lazarus Fuchs was the guy for whom we name regular singular points as Fuchsian singularities. And what Richard Fuchs did was to study an extension of the kind of problems that his father had studied. And that was to look at linear differential equations with regular singular points. But where, for example, the hypergeometric case has 3 regular singularities, he extended that to 4 regular singularities. Of course, if you have 3, you can put them at fixed places. Usually we choose 0, 1, and infinity for those 3. But once chosen, the 4th one can't be fixed. And if you let the position of that 4th one be some parameter that's called t in this case, then you can ask the question, if I allow t to move around in the complex plane, and I've mapped the complex plane into the Riemann sphere here, for what conditions on these coefficients of the system of equations you see in front of you are the monodromy data kept invariant? And I hope you've heard of the word monodromy before. It's expressing how a fundamental solution changes as you go around one of these singularities. Of course, you can always change your basis of solutions. So really it's the invariant data, the trace and the determinant of that change that matters. And those are typically called monodromy data. And he found conditions under which such monodromy data would stay invariant. Now, there are details here that I'm not giving you. There are also apparent singularities, in other words, where the solution is not singular, but the equation may be. And if you let that apparent singularity be W and T is changing, then what he found was in 1905, mind you, this equation that related W to T with some parameters, free parameters, alpha, beta, gamma, delta. And this turns out to be a major equation. It comes up in mathematical physics all the time. And it is now called, tragically, the 6th Painlevé equation. It should, of course, be called the Fuchs's equation, but never mind. It's one of these examples where an object is not named after the true discoverer of the object. So if you now consider this equation, there are other limiting cases. So remember, I mentioned the hypergeometric function, which corresponds to linear differential equations with 3 regular singularities. You know that you could take a limit of the hypergeometric equation where 2 of the regular singularities merge, and so you create an irregular singular point by the merger, and you get a limiting equation, which is the confluent hypergeometric equation. Well, you can do the same thing to this nonlinear equation. You can look at a merger of 2 singularities. We had 0, 1, infinity, and t. If I merge t and 1 by taking this limiting form, and then take epsilon goes to 0, and I've also taken the parameters going to some unbounded limits and scaled in a certain way, then what you find is a new nonlinear ODE, again with parameters alpha, beta, gamma, delta, new ones, new parameters. And this happens to be the fifth Painlevé equation. So you can do this limit over and over again. So another limit applied to these, to the fifth Painlevé equation would give you what's now called the fourth Painlevé equation or the third Painlevé equation. And each of these you can apply limits to, and you would get then what's now called the second Painlevé equation. And one more time, and you get to the first Painlevé equation. So I've shown you 6 equations now, which are labeled by the letters P with subscripts with Roman numbers. These 6 equations are actually canonical representatives of universal classes of equations, which are related to each other through linear fractional transformations or Möbius transformations of the dependent and the independent variables. Many of these have appeared several times in mathematical physics. The second Painlevé equation, for example, is famous in random matrix theory as the kernel of the distribution that gives you the Tracy-Widom distribution. And that is in the case when the parameter alpha is equal to 0. But what was interesting to the French mathematicians at the time of the turn of the previous century was the fact that these defined new transcendental functions. Now, what does that mean? It means that you cannot write down their generic solutions as, first of all, any algebraic combination of previously known special functions, not algebraic combinations of elliptic functions or ARA functions or whatever flavor special functions you might know and love, which are solutions of linear differential equations. They can also not be expressible as solutions of linear equations with those earlier functions as coefficients. And there is a class of those kinds of conditions which are called classical cases or classical solutions or classical functions, which were studied by Umemura, Watanabe, also Malgrange in France, and others. And that theory of differential Galois theory that got developed as a result of these kinds of questions are now known to show that indeed the solutions, the generic solutions of these equations are higher transcendental functions in the sense that I've just explained. So what do we know about their solutions? And despite the fact that we've now been working on understanding their solutions for more than a century, I'd like to put it to you that we don't know enough. So let me just give you a glimpse of some of the things that we do know before going on to explain the deeper theory behind these equations. So what do we know about them other than the transcendentality that I just spoke about? As I said, because of the limitations of this talk, I can't give you all the details, but I'm sure many things will be talked about during this focus week. This is a very old picture that I like to drag up every now and then. This is actually a snapshot in the complex T-plane, which shows the locations of the movable poles or poles of a specific solution of Painlevé 1. Don't worry about the jagged edges. The picture is supposed to continue forever. It's just where the numerics stopped. And you can see, for example, that the solutions have what is likely to be an infinite number of poles. If I were to change the initial condition at the origin, I think this particular one was taken with W being 0, and not 0, 0.5, and the first derivative being 0.4 at the origin. And you can see that there are discrete lines of symmetry in the way the poles are distributed. You can also show that if you approach certain special values, initial values, that the poles inside these sectors of symmetry that you're seeing in the picture will start moving away towards infinity. So you develop sectors where there are no poles whatsoever. Those are called truncae solutions. And then if those are one parameter families of solutions. But there are also specific unique initial values for which the solution has no poles in a contiguous region spanning 4 adjoining sectors, and those are called tree truncae solutions. I'm only talking here specifically about Painlevé 1, but it's known that similar solutions, similar features arise for the case of Painlevé 2, and I'm pretty sure they also arise for the other Painlevé equations. There are further very interesting solutions that we don't even have terminology to explain, to describe. Another feature you can see, perhaps not in this case, actually, you might start to be able to see it, but if you put initial condition right at the origin, for which you have a double pole at the origin, then you have a solution which is completely symmetric. That is, if you were to map one sector to another rotationally, you would get exactly the same picture again. There's another solution which is 0 at the origin, for which you get, you can describe a completely symmetric solution. But not much else is known until you go to asymptotics, asymptotic behaviors of these equations. So much of what we know about asymptotics and about connections between different directions of approach, for example, to infinity, comes from the study of the monodromy data. That is, the same way that Fuchs had looked at the linear problem with 4 regular singular points. When you go down to each of the other limiting equations, you have a linear problem, but now with not necessarily regular singular points, you have a higher degree of irregularity as you go down the list. But nevertheless, there are still data you can define to describe the solutions, the monodromy data, including the Stokes data around the irregular singular points. And there is a feature about these data, which is geometrically intensely interesting, at least to me, I hope to a few other people as well, which is that the monodromy data are related to each other. So if you were to go back to Painlevé 6 again, there were 4 points, you have monodromy around each, and they all relate to each other since we're describing the same set of solutions. And so there's interrelations between the monodromy data. And it turns out that they form manifolds. And for each of the Painlevé equations, you can write down the equation that defines the monodromy manifold. And they all happen to be cubic surfaces. That's already interesting. I think for Painlevé 6, that was pointed out by Iwasaki in 2002. And for the others, I don't know how new each one was, but they were tabulated by Vanderput and Saito in a very nice paper in 2009. And you can see, and I haven't explained here, but the characters that I'm calling omegas, they're all related to the parameters that occur in the equations, what I called alpha, beta, gamma, and delta earlier. And a lot about the fact that you have the types of solutions that I just spoke of can be described in terms of the monodromy data or special features on these cubic surfaces. You see, when I talk about initial values in a Painlevé equation, which is what defines where the poles are located and so on, that maps to a pair of monodromy data in the linear setting, and therefore to a point on one of these cubic surfaces. So something special happening in initial values is also something special happening on the monodromy manifold. So to give you an example of that, let me show you some pictures. This is the monodromy manifold, or at least my attempt to draw a real slice of the monodromy manifold of Painlevé 1. So remember that, if I can go backwards, if I look at the last equation here, the equation for Painlevé 1, which is at the bottom of this list, I could solve, for example, solve it for Z. That's an equation with denominators involving X and Y. So it's gonna be composed of hyperbolic sort of sheets with asymptotes when I attempt to draw it in the real XYZ space. And so what I've done here is to do precisely that, to draw the multi sort of piece diagram for Z as a graph as a function of X and Y. And in this space, in this monodromy manifold, if you look at the one on the left-hand side, that's the graph that I'm talking about for Z as a function of X and Y. If I slice through that graph by planes, so here's a plane, here's another plane, and at the back is another plane, which are given by where X is equal to Y and Y is equal to Z and Z is equal to X, then they all intersect at one point somewhere in the middle of this picture. And that one point corresponds to exactly to one of the symmetric solutions that I spoke about a moment ago. So there's some interesting, very interesting material available if you were to go to the monodromy description. But typically the monodromy data and this formulation in terms of linear problems has been used to solve asymptotic problems, a global connection data for the asymptotics of these equations. What happens in the finite plane, in the finite regions, is not typically, in my opinion, it has not been typically explored. Okay, so what I'd like to go to now is to tell you something else about these equations and their solutions, which unifies them in such a way that not only unifies the differential equations, but also unifies what turns out to be their integrable discrete versions. So this is an alternative view to the view given by the monodromy surfaces or by the linear problem. And I think, in my opinion, this is a stunningly beautiful mathematical view of what's happening with these equations. So in order not to overwhelm you with the detail, I'm going to start with one example, which is a very simple and pretty example to explain. So suppose I start with no knowledge of the Painlevé equations at all, but only with some algebra. So take, for example, a triangular lattice in the plane. So I have lines which are at angle 2 pi on 3 or pi on 3 with respect to each other. If I were to describe it in the language of reflection groups, what I have here is the lattice associated with the group A2. A for A-type, reflection group. There's a whole series of them that was classified by Carton and Killing. The 2 in the subscript is because I'm looking at the 2-dimensional case, and the superscript 1 is intended to denote the fact that I have an infinite reflection group here. So the idea is that what I want to do next is to describe dynamics on this lattice. What do I mean by dynamics? What I mean is that I want to be able to walk on this space to go from one triangle, a point inside a triangle, to a commensurate point in an adjacent triangle of the same kind. So how do I do that? Well, I'm going to take a point, as I say, take a translation, T, but that requires me to find a way of coordinatizing the points inside each triangle. So the way I'm going to do that is to assign a coordinate by saying that coordinate is 0 on this edge, another coordinate is 0 on another edge, and a third coordinate is 0 on the horizontal edge. And if I do that, oops, then what I have is a way to describe a point inside the triangle by taking the orthogonal projection of that point to the corresponding edge. So if this edge is given by A0 is equal to 0, then the orthogonal projection gives me a value of A0. It's the distance to that edge in that direction. And then I take a similar orthogonal projection to the other edges, and those give me the values of A1 and A2. Obviously, I'm using 3 coordinates to describe a 2-dimensional point, so there has to be a relation between them, and I'll come back to that. So this gives me a way then I can ask, well, what happens to the other values, the A1 and the A2? And to get that, all you need to do is to apply what you remember of Euclidean geometry from school, take orthogonal projections of the new point to the previous edges, and then consider what happens. And what you'll see here is that you get an equilateral triangle in this kite-shaped region. And so you can work out exactly that this long edge is A1 plus A0, and this vertical edge is going to be A2 plus A0. And so what I've been able to work out is the result of reflecting across that edge on those 3 coordinates. And it's given by what I just said. Okay, so what do I do with this information? I want to, oops, I just went through that. What I want to do now is to describe the fact that what these reflections across each edge of the triangle do is to construct a Coxeter group. This is for people who'd like to know about the connections with algebra and reflection groups. What you have here is actually 3 generators, which are given by the 3 reflections across the edges. And then there's the permutation, pi, which permutes these operations. They, in combination, satisfy these properties. Of course, the S squared is 1 because it's a reflection. You reflect once, reflect again, you go back to the beginning. There are relations between the S's because I was working on a triangular lattice. That exponent 3 is related to the angle between the edges. And this expresses the fact that you have this permutation of the indices, and that forms a Coxeter group. So the dynamics of the lattice now can be worked out just by using those reflections. So the way to do that is to realize that the initial triangle that I started with, which I've now labeled as delta, reflects across the spine of this diagram like a butterfly's wing onto the other side as S1. So this is the S1 image of that triangle. Then I have, a reflection across the horizontal edge. That gives me S2 composed with S1. But then in order to get a copy of the original triangle again, I have to relabel the nodes. And to relabel them, I needed that pi. And so finally, I get the result of applying the translation T1 from delta to delta prime. And so that allows me to write T1 in terms of those operations. And one last thing is that in constructing those orthogonal projections, what I was doing was calculating the legs, as it's called, of the triangle. And the legs add up to a constant, as you can see from this diagram. So I've called that constant K, but actually we take it to be 1. Okay, so now what we can do is to apply this construction to work out what T1 is explicitly, its action on the parameters. As I said, it's a composition of these 3 things. Each of them give me just a linear change in the parameters, and the sum of those 3 parameters turns out to be K, or equal to 1 later on. And so I have worked out exactly what the T1's action is on A0, A1, and A2. Now, these group actions, which I've just explained to you or tried to illustrate for you as actions on A0, A1, and A2, follow this table. But actually, this table only expresses the surface, what's happening on the surface of the picture I've showed you. There is a deeper structure behind this surface, which is given by the orthogonal complement of A21 in the Picard lattice, for those people who know what's going on here. And in this underlying dimension or depth or below the waterline, so to speak, what you find is that these also act upon those accompanying coordinates that describe what's happening in the iceberg below the waterline. And the coordinates for this below the waterline space are given by these Fs, F0, F1, and F2. And the reflection operations act upon those in these very simple birational ways. All of this can be found in Naomi's beautiful book called Painlevé Equations Through Symmetry, and I recommend it to you if you'd like to understand the details of what's happening here. So I can also look at the actions of translation on this additional hidden space. And when I do that, and noticing that in this other space, there's also a condition on the sum of the coordinates, F0, F1, and F2, what you find is now I've taken that constant to be 1. This is what I wrote down earlier in terms of the action of the translation. And now we define the repeated iterative action of T1 on those new variables, F1 and F0. What you find is a system of equations for those repeated iterations. And this is just a discrete dynamical system with the parameter T that comes from the F coordinates, the parameters A0 and A1 that came from the symmetry group that we just looked at. And this system of 2 equations is nothing other than discrete Painlevé 1. discrete Painlevé 1 is a term that we've heard from other speakers in this program earlier on in other focus weeks. Actually, I have to be strictly correct. The term discrete Painlevé 1 is used for a scalar version of this system, which you get if you're assuming that the u's and the v's are symmetric. In the Japanese school, the system of two components, u and v, is sometimes called discrete Painlevé 2 for other reasons that I won't go into here. So what we did was to start with just reflections and a very simple algebra of reflection groups, and out of nowhere comes a Painlevé equation. In fact, a discrete Painlevé equation. So in a sense, there is much deeper mathematics going on here, which goes beyond the search for new functions that the French school mounted at the end of the 1800s. There is another equation hiding in the background here. In fact, the equations for F0, F1, and F2 can also be written as differential equations if we differentiate with respect to t. And what we get is a system of this very symmetric looking system. I notice that I've switched to alphas, but they should be A's. And this is really another way of writing Painlevé 4. If you were to eliminate one of these components, two of these components, it turns out that F1 satisfies a scale version of the fourth Painlevé equation with parameters related to A0, A1, and A2. If I take the reflection operation on these variables, what you find is a transform version of Painlevé 4 given by G. Excuse me for a minute. And this is in fact nothing other than a Becklin transformation of Painlevé 4. So you get a lot of the information that is known about these classical equations from following the line of algebraic reflection groups. Okay. Oh, I'm sorry. I have to operate the slideshow better. There are other things that this framework gives you. In fact, it's well known that for special values of parameters, what I call alpha and beta in the original form of Painlevé 4, which correspond to special points in this triangular lattice, you get solutions that are rational solutions here, here, and so on. While there are hypergeometric type solutions on the edges of the triangular lattice. Okay. So in the case of Painlevé 4, these so-called hypergeometric type solutions are actually given by Whittaker or parabolic cylinder type functions. Okay. What about discrete Painlevé 1? This is the scalar form that I alluded to earlier, which is known as the discrete first Painlevé equation. I think for a special value of alpha here, it's also known as the string equation. It comes from Hermitian matrix models that many of you might know about already. But in my opinion, not much is known about the solutions. There are some beautiful solutions you can plot on the Riemann sphere. Here I'm taking a sphere of coordinates W and its iterate, starting with some points that are labeled, I think, associated with the color yellow, and then iterating for some value of alpha, beta, and gamma here. And I should mention the alpha, beta, gamma here are not the same as the alpha, betas in the equation for Painlevé 4. And as you iterate, you go from the yellow to the green to the turquoise to the blue and the magenta. So it moves towards the North Pole as you iterate. And then there are other solutions that look like they could be periodic, but they're not quite periodic, with shrinking and growing amplitude in the complex plane or shrinking towards the North Pole. So there's a lot to be learned about the solutions, but these are all open problems. How do you describe the behaviors of such solutions? I should mention that the name discrete first Painlevé equation was coined by Fokas, Itz, and Kitaev in their landmark paper in the 90s, early 90s. And they also showed that this equation is related to coefficients of recurrence relations for orthogonal polynomials with exponential weights, where the exponential is a function of a quartic variable. Okay, so as I said, there are many things to be found about the solutions. Many questions remain open. We know something about the asymptotics of the solution. Chris Lustry and I worked on the asymptotic behaviors of DP1, and there's some resurgent asymptotics in there. What we found was that there were two types of behaviors, which are given here. We call them type A and type B. And they lead to Stokes sectors, Stokes phenomena in the S-plane. But there's, again, more to be done. Okay, so what about discrete Painlevé equations? I have a very short amount of time now to talk about other equations that arise. I've just shown you how discrete Painlevé 1 arises, but that's just one type of discrete Painlevé equation. In fact, there are three types. DP1, discrete Painlevé 1, which I just showed you, falls into this first class on the left-hand side, where a coefficient function, n, is iterated on a line, but there are others which are iterated on complex spirals by multiplication by a parameter q, or iterated on elliptic curves. And so there are three flavors of discrete Painlevé equations, and within that description, Sakai found 22 classes of equations, and he likes to describe them in terms of a diagram which associates an Afal-Wall or Coxeter group to each particular class. The L here means it's the one of elliptic type. Mul means multiplicative or Q type. So the Q discrete Painlevé equations lie in this line. And then there's the additive types, which are at the bottom. And the classical Painlevé equations are the ones that belong in the bottom right corner of this diagram. And they were already known to have this structure shown by Okamoto in 1979. This diagram is slightly corrected from what Sakai gave in his original paper. It was corrected by Rains in terms of the degeneration arrows that you see here. So that was the initial value space, or the F space, if you like, in the case of DP1. There's also the symmetry group space, which is the orthogonal complement to this other picture. And you have an accompanying diagram for the symmetry groups. And again, the Painlevé equations lie in the bottom right corner. And the case we looked at was this case, the A21 case, which corresponds to Painlevé 4. So you can also do dynamics in these spaces. this is one of the things that I've been doing in recent years, starting with my work with Dijkstermaat in 2011. And there's a lot to be said with this description. In the initial value space, which is the analog of phase space, there are repellers for the solutions. There are also limit sets for each solution, and we can show some other properties, global properties of these solutions or equations, the generic solutions of the equations. But there still remains to be many questions to be answered. One of those perennial problems we have is to understand the global properties of these solutions. So the solutions of the discrete Painlevé equations are also transcendental functions, and we know almost nothing about them. One of the ways in which I've been tackling this in recent times is to consider the monodromy problem and the corresponding Riemann-Hilbert problem for the setting of these linear equations. So as I mentioned a little while ago, Foucault, Itz, and Kitaev had studied orthogonal polynomials with the weight function W, say. And it turns out that the Riemann-Hilbert problem given by these three properties here, if you take the 2x2 matrix that is analytic in the complex plane minus the real line, and which has a jump condition given by V as the jump matrix, which relates what's in the upper half plane to what's in the lower half plane. And you have a certain asymptotic growth or decay in the solutions as Z goes to infinity. Then it turns out that you can solve this problem uniquely under certain conditions on W, and the solution involves those orthogonal polynomials, orthogonal with respect to W on the real line. And this was worked out beautifully, and the asymptotics was given in detail by Dijft et al. In 1999 in a series of papers. This is just a picture to remind you that there is a metaphorical complex plane here with a cut in the middle, which is where the jumps occur. So these three properties are typical of Riemann-Hilbert problems, but for the Painlevé and discrete Painlevé equations, the jump conditions can get complicated, and the lines across which you jump may not be as simple as the real line here. One of the challenging issues has been, how do we formulate and solve Riemann-Hilbert problems for the discrete Painlevé equations, in particular the Q discrete Painlevé equations? And just recently we were able to make a little bit of progress in this direction, and I wanted to mention it before we stop. And that is to use Birkhoff's classical theory for Q difference equations to show that there is actually a solution for one of the Q discrete Painlevé equations. And there's some conditions I could go into, but I won't go into right now unless there are questions, which are the analog of Fuchsian type conditions for Q linear equations. And by Q linear, I mean this type of equation here. And I'm considering matrix equations, 2x2 matrices with polynomial matrix coefficients. And the case that we studied recently is a Q discrete version of Painlevé 4. Again, it can be written in a symmetric form like this, but instead of derivatives, what we have are iterates, denoted by these bars, the horizontal bars, which mean that T, the independent variable, is iterated by multiplication by Q. There's a corresponding condition on the product rather than the sum, as we had before, of the functions and the parameters. And what we were able to show was that the Riemann-Hilbert problem can be framed in this context And now the jump condition is a closed contour satisfying certain conditions. We can show that the Riemann-Hilbert problem has a unique solution, and that we can write down the monodromy manifolds as an explicit cubic surface. And this just appeared in Communications in Mathematical Physics earlier this year. And I couldn't resist showing you the cubic surface that you get. You can see it's cubic. The parameters, the coordinates are written as P, P1, P2, P3. The coefficients are theta functions. And there's something very interesting to be discovered about the solutions by studying the features of this cubic surface. So what about the dynamics of its general solutions? Well, that's completely open. And if you're interested in discrete Painlevé, let me write down some references. I don't want to be egotistical and mention only my work, but there isn't that much available in terms of review or detailed books or monographs on the subject, and here are just a few of them. So I'll stop there. Thank you.
Thank you, Nalini. Are there any questions about
that? Can I ask how you get the monodromy surface for Q difference equations?
Sure. So if I go back to here, the way we get it is by looking at the connection data across this curve. So there's the connection matrix across this curve. And there is a kind of an overdetermined feature to all the data that you have around this space. And the overdetermined feature gives you a condition that a certain determinant must vanish. If you look back at the original work on the continuous Painlevé equations, when you relate the data that go around the multiple different singularities, that relationship comes from the fact that they are not independent pieces of information. So in the same way, what we find here is a result of something not being independent of each other. And that turns out to be this cubic surface.
But the contour that you have, when you write down a Riemann-Hilbert problem, shouldn't it be some sort of a non-local analog?
I don't know what you mean by non-local, sorry. What I have is a solution which is analytic in the interior of this domain, and a solution that's analytic outside. I should not call it analytic, it's meromorphic with poles where the determinant of A vanishes. What we have is a jump function that connects the interior solution to the exterior solution. This is the primary part of the theory that was established by Birkhoff and his school. And so we have a connection matrix, which is just expressing, for example, if I call the solution inside y minus and the solution outside y plus, then y plus is y minus times this connection matrix.
Are there...
I have a question. So you mentioned that original Sakai's degeneration diagram was corrected.
Yes.
What was the problem with the original diagram? I believe I saw some extra arrow from A1 plus A1 affine.
Yes, that's right. So some of the degeneration arrows, I'm told, were, I don't know, they were wrong according to Eric Rains.
Okay.
So he just corrected some of those arrows, particularly in these A regions. And so it's really a minor correction.
Mm-hmm. Okay. Thank you.
Are there any further questions?
I should also point out that often people call this a classification, and Sakai himself says it's not actually a classification. And there are also equations that belong to, that have symmetry groups, for example, which are subgroups of the groups that are listed here. So for example, E8 has subgroups, a subgroup like F4, and there are equations that correspond to F4, which are not listed here explicitly.
Are there any more questions? If not, it just remains to thank Nalini for a very nice and clear talk as usual. And that concludes today's seminar. There are 2 discussion sessions that are happening tomorrow.